Today's lecture is going to be on neural network quantization. So last time I talked about many things. So in order for these neural networks to run in practice on physical hardware, like edge devices like cell phone or GPUs that run on robots like NVIDIA Jetson, and even high-end GPUs. If you want to launch really large models with hundreds of billions of model parameters, then you need to apply these techniques: quantization, pruning, distillation, and KB cache, compression, all these things. So last time the lecture was about pruning large neural networks, and today it's going to be on quantization. And there are so many things to discuss to make it fit in a single lecture. So I'm skipping a lot of details, but the references are available at the bottom of the slides. So if you want to learn more about the details, I suggest you go and read the paper. Or, to be honest, you can ask ChatGPT to explain these papers too. Okay, I'm just curious. So about the project, how many of you are using coding assistant tools like Codex or Cloud Code? Okay, almost everyone. Okay, that's good. That was exactly the purpose of the project, for you to get familiar with using Codex or Cloud Code. Okay, so yeah, last time we talked a lot of details about different pruning approaches, unstructured sparsity, semi-structured, structured sparsity, and other techniques. So today it's going to be on quantization. So the main question is, can we use fewer bits while preserving model quality and improve model deployment cost? So here, we're not going to change the architecture at all, but we're just going to change the underlying representation from floating point 16 to integer 8, 4, 2, etc. Okay, so what I mean by quantization, so let's say we have some real values represented using float 16, and if we quantize to, I don't know, integers, then we would, I guess the easiest thing to do is just to round it to the nearest integer. So for neural networks, this typically means you want to take as input a floating point tensor, output a lower bit integer code, and depending on the use case, approximate the tensor using that's used in computation. So I'm going to go into more detail later. So depending on whether you activate, so default is you quantize the weights, but you have an option to quantize the activation as well. So if you quantize weight and activation, you run computation using, for example, integer 8. And you'd use specialized GPU kernels for integer 8 general matrix multiply, which is much faster. If your hardware doesn't support that, or if it doesn't give you much gain, then you have choice to quantize only the weights, because that's the bulk of the memory. Activation doesn't count much towards the memory. So in that case, you keep everything using integer 8, but only when you compute that layer specifically, layer activation, you dequantize it and do floating point matrix multiply, and then you quantize it again. That still saves a lot of memory. Okay, so why are we doing this? The main benefit, so if you quantize the weight, then you significantly reduce the storage and inference. And activation, if you quantize the activation as well, you can do low precision matrix multiply if your GPU kernel supports that. So depending on the target hardware, if you run it, for example, on a cell phone, this may or may not be applicable. And some of the NPU vendors, I'm not going to mention the company name, but they don't support floating. They don't support integer for arithmetic. Some of you are laughing. Yeah, I'm not going to mention anything. But so it depends on the hardware. And you can even quantize the KB cache because, as we saw earlier, as you keep increase the context, the memory linearly just we need to keep in the memory additional key and value vector for each token. So it just keeps exploding, right? So we'd be better off quantizing it so we can save memory. You can also quantize the optimizer states, which take up a lot of memory as well. For example, if you want to do Atom, you need to keep in the memory a copy of the neural net weight and etc. So yeah. So what's a simple way to quantize these models? You can do a FI uniform quantization. So upon receiving a real scalar x, and we could choose a scale and a bias, so S and Z. So the integer code is you take your real number x divided by the scale S, round it, add in the bias, and clip it from minimum and maximum range. That'll be one of the easiest ways to quantize input number into an integer. Once you quantize it, how do you dequantize it? So it's basically everything reversed, right? So Q minus Z multiplied by the scale S. And of course, this may or may not be the same as the input original X because we have clipping and rounding, etc. So the notation is if I have tilde or hat, that's the dequantized value, and this may or may not be the same as original X. So you can do it with and without the bias Z. So in this case, if you just scale the input only, then typically your quantized value could be from -2 raised to the power of b minus 1. B is a bit width. We're going to talk about it later. To 2 raised to b minus 1, minus 1. Or if you incorporate this bias term, then typically the quantized code will start from 0 all the way to 2 to the b minus 1. So what is this b number? That's how many bits you're going to use to represent the input number. So, for example, if you use 8 bits, then you have 256 possible numbers after quantization, and you're going to use integer of range from -128 to +128.7. And if you use 4 bits, you're going to have 16 different outcomes, 3 bits, 8 different outcomes, etc. So in quantization community, this is the notation. W4 A16, that means weights are quantized to 4-bit. Activations remain 16-bit precision. So you only quantize the weights. This notation means the weights are quantized to 8 bits, and so is the activation. Right? So whenever this number is not 16, that means you're going to use specialized hardware GPU kernels for example, in this case, 8-bit general matrix multiply. So we talked about a simple quantization scheme. So you introduce scale and some bias, and to dequantize, you do the reverse. And for implementation, if you wanted to make, let's say you have a linear layer with matrix multiply, then W hat is your reconstructed or dequantized weights. So one thing you can do is absorb the scalar into X, so it's fused. Yeah, I already talked about this. So once again, for example, if you have W4 existing setting, the weights are stored using 4-bit. And for actual computation, let's say we have these layers, and we're looking at somewhere here in our computation. Everything here is stored, all the weights are stored using 4-bit. To compute the activation here, we're going to temporarily upcast this or dequantize it to 16-bit and call general matrix multiply with using 16 bits. And then we're going to dequantize it again. We're going to quantize it again to 4-bit, and only when we compute the activations, we're temporarily going to dequantize it to 16-bit. And when this number is not 16, we run computation throughout using 8 bits or 4 bits without dequantizing anything. So we talked about the scale number. You could have as simple as per tensor scale, or you could group it by output channel, or define your own groups where these have different scales. And there are many different practices. And we're going to generalize this notion later. Okay, so can we introduce some framework? So let's say we're doing some k-bit quantization. So this function q takes a real number, real vector, with some auxiliary input, and outputs binary vector of size k times d. So each real number gets mapped to k bits. And we have d such numbers. So we have k times d binary vector, and some parameters. So this data stores some quantization parameters, such as scale, bias, or codebooks. We're going to talk about this later. And this function dq is the dequantizer, where it takes the binary representation and these auxiliary parameters and tries to reconstruct the original input. So given a tensor in d dimensions, at least for now, I say at least for now because I'm sorry, but different papers use different notations. So here, this underscore is to denote this is the quantized representation. So the reconstructed one, we're going to use tilde or hat. Okay, so what's the simplest way to do this? Simplest way to do this is to round to nearest uniform. So we're going to create a uniform grid. It has two parameters, minimum and maximum. And this grid is for every I from 0 to 2 to the k minus 1, it's going to jump according to this step size. So how do you round it? You choose the grid index that is closest to the input x. So equivalently, the grid index is so this is the grid, the actual nearest neighbor in the grid, right? So you create equally spaced grid, M, capital M, and let's say your x is here. This guy is this number here. And what is the index here, I star? That's this number here. Index starting from 0, 0, 1, all the way to 2 to the k minus 1. And the reconstructed one is going to be this number, x hat, right? So how do you compute x hat? You just compute the index, I star, and walk this much in the grid, right? Okay, so how do you determine the quantization range? So we have a predetermined fixed bit width k, and you have some choices. You could do min and max, or you could try to, one sensible thing to do would be, I don't know, try to ignore these extreme points, treat them as outliers. What do you think will happen? Just intuition-wise. So actually, what happens is this turns out to be a bad idea. These outliers really matter. So remember, in unstructured proving, people found out you can make the network 90% sparse without losing accuracy, right? And their objective was, okay, if the weight is small in absolute value, you just prune to 0. So it turns out these outliers carry most of the information. Well, I say this with the caveat, depends on your model, but this is not a good idea in general. Okay, so let's introduce some other notation. So if you have a linear layer size d in by d out, and x is activation of size n by d in, wj corresponds to the output channel indexed by j. So one of the columns in the matrix. Let's call this guy wj. Okay, so what is a good reconstruction objective? Besides just rounding. One thing you can do is to minimize the reconstruction error. So this is the original full 16 number. This is the dequantized reconstructed version. And this would be one sensible thing to do. But if you have access to small numbers training data, then on this calibration data, you can try to minimize the reconstruction error of the output activation. So this is saying a good dequantized or good quantization scheme should preserve the output activation, not just the weights. Because we want to be able to represent or mimic the original network's behavior by preserving the output or result of the linear map. Okay, so let's define the difference between the reconstructed version and original version as delta W. So we can rewrite by grouping with x. That's going to be Frobenius norm squared of x delta W. And unpacking this square, we have trace of delta W transpose x transpose x delta W. So using this notation here, Wj is the jth column of W. So we can write the same thing equivalently as sum of output channels or output dimensions. Delta Wj transpose H delta Wj. Sum of all output channels J. So it decomposes over the output columns. Okay, so let me show you an example, a counterexample showing rounding to nearest integer is not a good idea. So let's say W, one of the output column W is two-dimensional, and we're using 1-bit grid. So it's going to be 0 or 1 after quantization. And we're given this H matrix. H is, by the way, X transpose X. And this weight column is 0.4, 0.6. If we do rounding to nearest, we have, after dequantization, 0 and 1. Right? We're reversing the rounding. And delta W is, let me show you that W is reconstructed version minus original. So this minus this is this vector here. And if we look at the objective, that's 0.48. How about if we use some other quantization and put everything to 0? If we dequantize it and the output is all zeros, then delta is this guy minus this guy, so negative 0.4, negative 0.6. Compute the objective, that's 0.24. So our objective is smaller actually compared to rounding to nearest. So it turns out the best rounding decision should take into account this H matrix, or the data, or the activation. So we shouldn't just blindly look at the weights, but also take into account the data. Okay, so this paper, ADA round, they introduce a learning problem where for each weights independently, they learn this V matrix. So here is the optimization problem. So here, they want to learn this V, where if you dequantize using V, it directly minimizes our original objective. And this regularizer encourages this number to be close to 0 or a 1. So we have a regularizer that squashes the inputs to either 0 or 1. But in practice, this is very expensive because you need to optimize one continuous variable per weight. And if we have 300 billion, this is not going to work as is. So you can use some regularizers. So, for example, if you have a value that's in between, you get penalized a lot. And if you have value that's close to 0 or 1, you get less penalty. So you're going to get high penalty if you are somewhere here. Okay, so what's more practical algorithm? So GPDQ is used quite a lot. So this is an important contribution. So it's one of the post-training weight quantization method where you iterate between quantizing one coordinate at a time. So sequentially, so given each upper column, it sequentially optimizes different coordinates of WJ in coordinate descent style fashion. And when one entry is fixed, it updates the remaining entries in WJ one at a time. So what I mean by post-training weight quantization, so there are two, I guess, two different areas where people approach quantization. One is, after quantization, are you allowed to fine-tune the network, the quantized network, or not? So post-training approaches, you don't retrain the model using data. So practically, it's really hard to obtain the training data that was used during training. So if you could do quantization without having access to the training data, that will be more practical. And nobody wants to run training because it takes up so much time and lots of GPU. Okay, so let's just drop the output column index and just consider one column in the weight matrix. So suppose the first coordinate, W0, is quantized to W hat. And what is the quantization error induced by this quantization of the first coordinate? That's basically the difference between the dequantized first coordinate minus the original weight. So in short, we're going to write it as standard basis vector where it's 1 and all zeros. And Notice we changed it to small delta because we're just talking about a single output column. Okay. All right. So now the objective. Okay. Let's just go back. This used to be our objective. Sum of our output channels. Delta J, delta WJ transpose H delta WJ. So we're just looking, and this nicely decomposes over output columns. Since we're looking at a single column, we just need to look at the corresponding entry in the sum. Okay. All right. So this is our objective. So we have a vector in D in dimension, and the objective is delta W transpose H delta W, subject to the constraint that if you take this vector, first entry has to be equal to this number because first entry is already quantized. It's fixed. So you have a choice to optimize from dimension 2 to dimension n, but first entry has to be fixed. So far, easy, right? And intuition-wise, you can think about it as absorbing this rounding error in the first dimension into the rest of the entries. So you create a shock in the first dimension, and you need to absorb it from other dimensions. Shock meaning quantization error. Okay, so let's take this objective, and if you don't know what I mean by Lagrangian and stationary points, that's fine. I covered this in the graduate level machine learning class, but it's okay if you don't know what I mean. Okay, so to solve this constraint optimization problem, I'm going to formulate a Lagrangian. So we have primal variable delta W, dual variable lambda. Dual variable, you have one dual variable for one constraint. So you have a single dual variable here. And this is vector valued variable. So this is the objective, right? I copy pasted the objective plus dual variable and the constraint, and take the gradient, set it equal to 0. We have these two formula. And using the constraint, solve for W here. Let's call it W star. So W at optimality, lambda at optimality must satisfy this equation. Okay, I'm going to plug it in back into our formula here, obtained by stationarity of Lagrangian. And this is the relation that must be satisfied by delta W star, optimum primal point. Okay. All right, so seems like we have an algorithm now. Okay, so if the first entry in the vector variable is fixed, we have a way to find the optimal deltas from dimension 2 all the way to dimension n. So the algorithm would be fix one coordinate at a time. Right? Okay, so at step 0, we quantized the first coordinate, and they gave us update for the rest of the entries. At step 2, we freeze first two coordinates and repeat and repeat and repeat until we fix everything. So that's the algorithm, and very simple, right? So it's just doing coordinate descent. And one implementation detail is you never want to do matrix inversion So you want to do something like Koleski-based update and batching tricks, but it's just minor detail. So here is some results. So RTN is round to nearest. So floating 16 is the original network, and using 4-bit widths, not much of difference. And how about 3 bits? Wow, the difference is quite significant. 500 to 8. All right, so AWQ is another algorithm. It targets weight-only quantization, and the idea is if the calibration activation, so this is the calibration data, calibration activation reveal which inputs are important, then you want to put more weight into quantizing the weight, the corresponding weight. So you want to introduce this diagonal matrix S that measures sensitivity along these channel dimensions. And without quantization, it's the same operation. You want to multiply S inverse and S, but based on the sensitivity, you're going to pre-multiply post-multiply to X, pre-multiply to W, and it makes a difference when you actually quantize. So as opposed to quantizing S, you quantize SW, and at inference, you compute it like this, as X times S inverse, and quantize SW. So it seems like a NOVA, but if you quantize this guy, and this guy, sorry, this is weight only, sorry. You quantize this guy, then it makes a difference. So this S incorporates the sensitivity based on the Frobenius norm, sorry, L2 norm according to the column vector of S. So yeah, I'm going to skip some details because we're going to generalize this. All right, so we talked about this. So one of the big problems in quantization is how to deal with these outliers. So turns out if we just treat them as outlier and just omit it from, or don't pay attention when we quantize, then we lose a lot of accuracy because these carry a lot of important signal, and these are close to zero, so they don't carry much information, turns out. Yeah, so let's look at this figure. So for these two matrices, output projection, down projection, if we look at absolute weight value, 99% of the weight, 99.9%, 99.99%, they're all close to zero. So these things in the tail, they have actually high value, and most of them is concentrated near zero. So, for example, if we do uniform greeting, then that's going to create lots of problem because the greeting resolution is going to be very sparse towards the outlier points, and it's going to do a fine greeting near zero. So this is another influential paper, not just theoretical work, but this is almost always used in almost all quantization these days. So it's very important. So idea is to do rotation. So for an orthogonal rotation matrix R, the L2 norm is preserved. And the idea is, so let's say X is two-dimensional. If we have, so I'm just giving you an intuition, something that's close to 0 in one dimension and has very large value along one direction, if we rotate, they're going to have their energy or norm spread out through the two dimensions. That's more or less the idea. So for example, here it's going to be close to 0, like 0.001. Here it's going to be, I don't know, I'm going to just create a random number, 15. Once you rotate, this is going to be, I don't know, 7 by 8 or something like this. I'm just creating some random number. Okay? So if we rotate, they are more evenly spread among different coordinates, and they require smaller dynamic range, and they're easier to quantize. So there was a theoretical work that approached this from signal processing perspective called incoherence processing. Last year we went into all the details and proved theorems, but this year Professor ChatGPT told me to erase all the theorems, talk more about new stuff. So I followed his advice, his or her advice. Okay, so this matrix U and V are orthogonal transformation matrices. And take this matrix W and H. H, remember, is X transpose X. This is the weight. What we're going to do is we're going to pre-pad and post-pad the matrices with these orthogonal matrices. And if you work out the details, because they're orthogonal matrices, there are multiples. So if you multiply V transpose V, for example, it's going to be identity matrix, and all the nice properties are going to hold. And I think this should be V. Let me double check and fix it later. So quadratic reconstruction objective that we looked at before, that's exactly identical. Just because of the property of the orthogonal matrix. So we're going to rotate these matrices and rotate back during inference. So we're going to rotate, quantize, and when we need to compute, we're going to dequantize. So what's nice about this is, if you look at this diagonal line here, before this processing of pre and post padding with these orthogonal matrices, if you compare before and after, these large values became very small. So all the points are below the diagonal, meaning the maximum absolute value weights is reduced after incoherence processing. Just a fancy word for padding these matrices, or pre-multiplying and post-multiplying with orthogonal matrices. And my students, I call this as a shock observer. So this matrix is going to get shocked when it gets quantized. So these orthogonal matrices absorb shocks that happen during quantization. If you're interested in the theory, just read the paper. It's not difficult. So Quarad also applies this technique to activations. So after orthogonal rotation, these outliers become flat out across different dimensions. And just to go through the so this is the orthogonal rotation matrix. So this is our linear layer x times w. If you do xr, r transpose w, because they're orthogonal, these are identical. But when we quantize, they make a difference. Quantize xr, quantize r transpose w. So rotations make weights, activations, KB cache less outlier heavy and reduces the overall quantization error. This doesn't solve all the problems, so we're going to talk about non-uniform quantization, vector quantization, etc. So KB cache, as you know, grows linearly as we increase the context size. So a new token comes in, you compute the attention, you append this new KB vectors, and you read these consecutive keys and values and generate the output next token. It repeats, right? So it contributes a lot to the peak memory. So it has to do with number of layers, sequence length or context size, hidden dimensions, and bytes. So can we do something about the bytes from flow 16? So main benefit is using the same amount of memory. If we can quantize this, you can increase the context size. So this paper proposed for the key cache quantizing along the channel dimension, and for the values you quantize per token. It leads to less quantization error. But specific detail is not important. The important thing or the takeaway for students is you can also quantize the KB cache without losing much of the performance. Why? Because the KB cache memory is also a function of bytes. So if we can cut this by a quarter, that's a significant saving. Okay, so rotation is good, but it doesn't solve all the problems. So for example, if we have this distribution of the weights, then if we do uniform grading, clearly it doesn't represent the data very well. So a better way to do this is to do non-uniform grading. You allocate more bits where data is dense. Instead of using scale and 0 point, we're going to generalize it further and introduce this concept called code book. So each scalar weight chooses one of the codebook entry. So AI is the corresponding index in the codebook. So given a weight, which codebook do you belong to? So dequantized weight W hat is actually the corresponding entry in the codebook. Or you can write it equivalently using an assignment matrix. It's a binary matrix of size d by 2 to the k. 2 to the k is size of the code book. So the objective is following. Given a weight W, you want to minimize the output difference between P times C, subject to the constraint that P times column vector 1 is equal to column vector 1. Meaning each W here must find a single entry in the codebook. It cannot find 0 or 2 or 3 entries. It has to get assigned to a single entry in the codebook. It's okay for a codebook entry to get multiple W's mapped to it, but it's not okay for the W to map to different coordinates, different codebooks. So if you know k-means, this is exactly k-means objective with 2 to the k clusters. Okay, so these following works introduce some weighting in the k-means objective. So Squeeze LLM, for instance, uses second-order loss approximation. So loss using this reconstructed weight W hat is original loss plus gradient plus second order term, but we're going to assume this goes to 0 because we have sufficiently trained the network without any constraints. And what they do is they just approximate this Hessian using a diagonal matrix, diagonal Fisher approximation. So now the objective becomes Fisher approximation weighted k-means objective. So here they introduce some weighting term here. So important weights as measured by Fisher is going to receive larger penalty when quantized poorly. And another paper, pretty much similar idea, but it weights the reconstruction error by the end loss gradient. So if one of the dimensions plays an important role in terms of the actual loss, then we pay a lot more weight for quantizing that specific weight. So for output column J, gradient with respect to, so given a single data point, gradient with respect to Wj is going to be, so by the way, Z is the output activation, dLdz times xi transpose. And from the objective here, we can unpack this one bit over each dimensions. And after massaging a little bit, it's basically the difference term times this intermediate block diagonal matrix F, which is dLdW transpose. So turns out the difference is in Squeeze LLM, this is Fisher approximation diagonal matrix. But if you look at the contribution of the weight with respect to the loss, then turns out you have a block diagonal matrix that's weighting the k-means objective. And how do you solve this? So we're going to optimize assignment matrix P and the codebook simultaneously. So given P, we optimize over the codebook. That can be done in closed form. That's just least squares. So when P is fixed, so we have the constraint here, right? P1 is 1. When P is fixed, optimization over C can be done in closed form using least squares objective. And how do we do assignment over P? This is an integer program, so it's discrete, and we can do coordinate descent where we assign one variable at a time. So does it make a difference? So y-axis is the perplexity, which is lower the better. X-axis is number of bits, and this dotted black line is the original network's perplexity, about 5.2 or something like that. And if you jointly optimize this Fisher block diagonal matrix, weighted k-means, then it performs much better than squeeze LLM or other variants. So how much performance drop are we expecting? So original network using 16 bits has this performance based on 2 billion, 13 billion, 70 billion model. And if you use 4 bits, it's more or less the same. So if you start to use 3 bits and 2 bits, you observe a significant performance drop. But 4 bits gives you roughly factor of 4 saving in memory, but the performance is pretty much the same. So there's no reason to not do this. Okay, so we just talked about scalar optimization, non-uniform scalar optimization, quantization. So you can generalize this further to vector quantization. So pictorially, it looks like this. This is uniform grading, and non-uniform quantization in 1D looks something like this. You don't take into account other dimensions in quantization. But in 2D, vector quantization looks like this. So here, multiple weights get grouped to a vector. So we're not mapping one scalar to another scalar. We're mapping group of weights to a vector. So there are many different ways to do this, and I'm not going to go into much details for vector quantization, but we can apply the same idea. It's just the generalization we need to make is we extend the codebook to be vector, not scalars. Then just same idea, optimize over the P matrix, the assignment, and the codebook. Codebook optimization can still be done in closed form. Using 4 bits, you don't see much drop in the performance. Even 3 bits, you get modest drop in performance. 2 bits, quite significant. So how about the throughputs? Of course, if you use 2-bit optimization, uniform, non-uniform vector, you get about 300, 200 tokens per second. And original throughput was 16 tokens per second. And if you use 4 bits, you get a modest improvement, like 2 to the 3, like 2.5x throughput increase. But for 3 bits and 4 bits, 70 billion model outputs out of memory error for this specific GPU. I think this is using RTX Ada GPU. And the trade-off is vector quantization always better than non-uniform scalar quantization? Yes and no. So the trade-off is it's more accurate to do vector quantization, but code books are bigger, and the throughput, if you compare this to non-uniform scalar, is smaller. Compare these two numbers. So you can be more accurate, but the throughput is going to be smaller. Why? Because let's say you are not quantizing the activation. So what you need to do to compute the output activation is you need to map the quantized weight to dequantized weight, and you need to load the codebook entries and translate. And each codebook is heavier, so it might take multiple instructions to fill the memory with vector codebooks. So it can be slower. Okay, so we talked about a lot of different techniques, but in the interest of time, we had to skip lots of details. But we talked about a lot of things. So uniform, scalar, and vector codebooks, non-uniform, scalar quantization, rotations. So to give you the current trend, pretty much everyone uses quantization, and the dominating approach is no training or fine-tuning after quantization. And one thing we didn't get to discuss is today's lecture, we just assume everything's either going to be 4 bits throughout or 8 bits throughout or 2 bits throughout. But the better thing to do is called mixed precision quantization. So can you allocate different bits to different layer weights? What is the optimal allocation? That's the optimization objective. So let me finish, and if we have time, we'll come back and talk more about mixed precision quantization. Okay, so let's do a brief summary. Quantization maps real value tensors to low bit codes, and you can decide to quantize just the weights, which is the bulk of the memory, or also do activation quantization. That makes sense if your hardware supports efficient matrix multiply in 4 bits or 8 bits or 2 bits. And what is the typical objective? The common approach is to look at the output activation before and after quantization. And we talked about popular approaches like GPTQ, where you freeze one coordinate at a time and solve it using closed form updates. And KB cache quantization, KB cache size is also depend on number of bits. So just do 4-bit quantization, you save 4x immediately. And there are trade-offs between non-uniform scalar quantization and vector quantization, trading off accuracy versus throughput. So we started off saying you can do nearest integer rounding, but turns out it's not a good idea. So the objective that we used is the output activation difference, and talked about different optimization quantization schemes like uniform, non-uniform, scalar quantization, and vector quantization. Okay, so just give me about 1 minute to find the slides. Okay, so here's a result of what mixed skin quantization looks like. So this number here corresponds to layer index, layer 1, layer 2, etc. And let me show you the full picture. Okay. All right, so just look at this figure and this guy to the left. So one block here represents to one matrix. So this number is layer 1, layer 2. For each layers, we have WQ, WK, WV, out, up, gate, down matrices, right? For LLMs. And for each block here, we're going to make a choice. So we could do 2, 3, 4, 5, 6, 7, 8 bit non-uniform scalar quantization, or we can do vector quantization, or we can do something called trellis-coded quantization, which we didn't cover today. And they come with different trade-offs, throughput versus accuracy. And the shapes represent which quantizer you're going to use, and the colors represent how many bits to allocate per each matrix. So after optimization, this is the fully optimized mixed precision quantization result. So you can see different weights according to different layers get allocated to different quantizer for the optimal speedup. So the original perplexity was 7.7. Sorry, this is one of the baseline, and get about 2.3 speed up, but you can increase to about 3.17x speed up with better perplexity. And one thing that I mentioned briefly last time was graph optimization. So can we find the mathematically equivalent subgraph that may or may not run faster on a target hardware? So one famous thing is weight fusion. So depending on the hardware, it may be faster to fuse all the QKB weights and then split the results, as opposed to matrix multiplying one by one and adding up the results. So we could also optimize over this space of graphs as well. So this block here represents we're going to fuse WQ, WK, WV for starting from layers 3 to N, but leave these guys alone, only fuse Q and K and V. And for example, up and gate, always mix it for all layers here. So the space of optimization is really, really large, not just how many bits to use throughout. You can do it much better, allocate which bit to which of the matrices in which layer, which type of quantizer, and do you fuse the matrix multiplies or not. All these are space of optimization. So how do you do this? Okay, so we want to formulate an optimization problem. So PLQ is a Boolean variable. So this term is the loss after quantization, and this is the original loss. So you want to minimize the difference in the loss before and after quantization, subject to the constraint that says for all layers, you need to pick one of the quantizer. You cannot pick two. And using the quantizer for that specific layer weight, compute the average bits used. And this is the dimension of W, D in, D out. And you select your chosen quantizer. And this can compute the average memory spent for representing the matrix, and you would have a memory constraint, something like it has to fit in your cell phone or something like that. Of course, we cannot use this objective as is, so we're gonna simplify the objective a little bit. So, like the previous lecture, we're going to use a linear surrogate. L of LQ is, for that specific layer, if you use that specific quantizer, what is the drop in the loss? So that measures the importance of that layer using that quantizer. So we have linear objective and linear constraints, which can be solved with combinatorial optimization subroutines. This can get stuck and run forever. It's an NP-hard problem, but most times it works. When it works, it finds the optimal solution. All right, so another thing I didn't mention is, okay, so I said you can also optimize over the choice of merging these networks, right? So this is mathematically equivalent as opposed to doing 3 matrix multiplies with small matrices. Can you just concat them, do 1 matrix multiply, and split the results, right? So as opposed to looping over or grouping the variables in terms of layer ID, you can group the layers that are mergeable. So we're now optimizing over the space of groups where it makes sense to group or not. So the optimization algorithm or the objective is pretty much the same, except that we are no longer looping over layer indices, but we are looping over different groups. So this gives you an algorithm where you can find the optimal mixed scheme quantization routine, where it automatically assigns the optimal type of quantizer, how many bits to allocate, and whether to group them or not on the target hardware. All right, so that's pretty much the state of the art. This paper came out in December, and we're using this with Samsung, so the next generation Galaxy model can support really large language models. All right, that's it for today's lecture. Thanks.